All right, so we're going to head on to our next speaker now. To make sure that this is up, and that will be Jared Longfox. So if we got you here, please go ahead.
All right, can everyone hear me?
Yes.
Awesome, thank you. All right, I will get started. Yeah, hi everyone. My name is Jared, and I am the geotechnical specialist at the Class Exolith Lab at the University of Central Florida. This talk will discuss a statistical examination of the effects of funnel size on mass flow rates of lunar regolith simulants LHS1 and LMS1. Next slide, please. And in the interest of time, we'll just kind of skip over this one, but it's an overview of what we'll be talking about today. So next slide, please. So, for a little bit of background, we know that the moon has two distinct geologic provinces, namely the lunar highlands and the lunar mare. The regolith in these provinces each has a unique composition and is expected to have different physical properties that present mission-specific challenges imposed by this varying regolith behavior. Excuse me. So lunar ISRU systems will likely involve the automated transport and storage of regolith. My goodness, excuse me. And need to account for any differences in the relevant parameters affecting this regolith storage and transport, such as mass flow rates through various processing systems. Since there is no bulk returned regolith available for testing, we need to use high fidelity terrestrial analogs, and that is exactly where Exolith Lab comes in. So next slide, please. At Exolith Lab, we are a nonprofit organization who create simulants based on an accurate mineralogy in terms of both composition and grain geometry, which we expect to give us an accurate representation of these regolith properties. Our goal is to create the most high fidelity regolith simulants possible while balancing the cost, availability, and safety of our simulants. Used here are our Lunar Highland simulant, LHS1, and the Lunar Mare simulant, LMS1. For more detailed data on these and more of our simulants, please visit our website, exolithsimulants.com. Next slide, please. So, as I said, we used LHS1 and LMS1 here, and LHS1 is our Lunar Highland simulant that is compositionally dominated by anorthosite and glass-rich basalt. This simulant has a mean particle size of 60 microns and median of 50 microns. Next slide, please. LMS1, our lunar mare simulant, has a more mafic and mineralogically diverse composition than that of LHS1, as shown in the table here. The mean and median particle sizes of LMS1 are slightly smaller than that of LHS1 at 50 and 45 microns, respectively. Next slide, please. So, the goal of this study was to quantify and statistically compare mass flow rates of these two simulants in terms of grams per second. To do this, we used funnels of varying outlet diameter but identical wall angle, and we measured the flow rate at which a massive simulant exits these funnels. The funnels used here have diameters of 25 through 55 millimeters, and all of these diameters are within half a millimeter of their desired size. So for each of these 7 funnels, we put 5 samples of 500 grams of each simulant through them and collected a total of 35 samples of mass flow rates for each simulant. During testing to prevent bridging or clogging of the funnels, we used vibration motors to give this consistent and uninterrupted flow. Next slide, please. So shown here in the picture on the right is our testing equipment. During each experiment run, cumulative mass data is sent from a serial communications capable laboratory balance that log to a laptop that logs this data along with the time that has elapsed since flow began. Next slide, please. So once we have this data, we are going to be comparing these mass flow rates of LHS1 and LMS1 with a two-tailed t-test that compares the means of the flow rates for each respective funnel size. So this means that data for LHS1 and LMS1 for the 25 millimeter funnel will be compared, the 30 millimeter funnel for LHS1 and LMS1 will be compared, and so on. But note that to be validly compared using a t-test, each group must be normally distributed, which we test with the Shapiro-Wilk test, And the groups must also have homogeneity of variance, which we test with Levine's test. And if these conditions are not met, then the t-test cannot be performed on the data validly. Next slide, please. So we run these experiments on LHS1 and LMS1, and we made this plot of the 5 sample flow rates that were measured for each funnel outlet size for LHS1 and LMS1, with LHS1 given in blue and LMS1 in red. Next slide, please. So the plot on the left is a graphical summary of the table on the right, but what this shows is the average of that last plot, those 5 samples for each one, averaged with plus or minus 1 sigma error bars, just for reference. Next slide, please. When we run the t-test, we get the following. The table is our results with items in bold and highlighted text, indicating a statistical significance. In the case of Levine's test, we see that the data for each funnel size for each simulant has equal variance, but we do not see normality in the LHS1 50 millimeter and LMS1 45 millimeter funnel data. So those 50, and 45 millimeter data are not able to be compared via t-test. So the results of this t-test on the sizes that can be validly checked shows that the mass flow rates of LHS1 and LMS1, 25 through 40 millimeter mass flow rates, are significantly different. The 55 millimeter mass flow rate was also tested, but was found to not be significantly different. Next slide, please. So for just as a quick visual check, non-quantitative, but still good to have a gut check, I suppose, we have the same table on the left with a familiar plot of the average flow rates on the right. Again, LMS1 is in red and LHS1 is in blue. So we can see here that the error bars for the 55 millimeter data have significant overlap. So at least to me, it makes a bit of sense that these are not significantly different when the rest that were tested, 25 through 40 millimeters, are significantly different. Next slide, please. So, what does this all mean? What have we learned here today? We saw that LMS1 has a significantly higher mass flow rate than LHS1 for funnel outlet diameters of 25 to 40 millimeters. And we attribute this to differences in mineralogy in terms of both composition and grain geometry. Also remember that LMS1 has a smaller mean and median particle size, so that could be an additional factor contributing to this as well as differing mineralogy. We also noted that the mass flow rates of LHS1 and LMS1 for the 55 millimeter funnels are not significantly different, which we attribute to a change from a flow-dominated system to a regime dominated by slope failure dynamics. Next slide, please. So, from this, we conclude that differences in mineralogy lead to variation in the mass flow rates of lunar regolith simulants, HS1 and LMS1. Variation in this ISRU relevant characterization of regolith rheology, try saying that 5 times fast, needs to be accounted for all aspects of ISRU system designs that are going to incorporate regolith transport and storage. Our next steps are examination of mass flow rates as a function of funnel outlet diameter, all at once, pending investigation of grain size assumptions for these empirical models. Again, we are happy to work with you to create custom simulant orders and do custom geotechnical testing on these orders at Exolith Lab. So for more information, feel free to contact us at our website. Next slide, please. And finally, I would just like to thank the team at Exolith Lab and CLASS, the Center for Lunar and Asteroid Surface Science, as well as NASA Survey for all of your support. Next slide, please. And I don't know that there's any time for questions, but if there's not and you would like to reach out to me personally, my email is given here.
All right, thanks so much.